Okay, hello everyone in a new video. So we have reached part 5 of chapter 2, which is the chapter of electric voltage for grade 10 students. Then we have reached section number 9, and the title of this section is given by the importance of an electric switch. Then the first subsection that I want to talk about is given by 9.1, and the title of the subsection is given by switching on and off an electric circuit. So now here in each subsection we will discuss one role or an importance of an electric switch. Okay, so switching on and off an electric circuit. Then the first role that we have seen previously is that, now notice that in this case the switch K is connected in series with the battery. We know that in this case the role of the switch is turning on and off the given electric circuit. Then let me write a switch can turn on and off a given electric circuit Now this switch can operate in two modes. So in this case it is open. Now if the switch K is closed, we know that it acts as a connecting wire, and we know how to deal with closed electric circuits. Okay, so we can use the law of addition of voltages in order to determine the voltage across any electric component. But now in this case we can talk, if the switch is open, we can talk about the following voltages. So we can talk about, suppose that the voltage of the battery is given by 12 volts, okay, and we don't care about the voltages of the lamps L1, L2 and L3 simply because the switch K is open. So we can ask what is, sorry, so now suppose that UPN is equal to 12 volts, and we are interested in discussing the voltages. Now recall that K now is an open switch, and we are interested in discussing the voltages across different electric components, for example across the wire, across the lamps UBC, UCD, UDE, and more importantly the voltages UEF and UFE across the open switch. Okay, so first of all let me say a disconnected terminal can be considered as a connecting wire. Now notice that because the switch K is open, the terminals E and F are now disconnected. So from P to E, this terminal from P to E is now disconnected from the point F. So in this case, when we have a disconnected terminal, it can be considered as a connecting wire. So in this case, okay, PA is a connecting wire, AB is a connecting wire. Now from P to E, this all of it can be considered as a connecting wire. Why? Because simply the terminal E is now disconnected from the point F simply because the switch K is open. And now in this case, because from B to E is considered as a connecting wire, then from B to C is considered as a connecting wire, from C to D is considered as a connecting wire, D to E is considered as a connecting wire simply because the terminal E is now disconnected. Now what about the voltages UAB, UBC, UCD, UDE? So all of these voltages are set to be 0 because they act as a connecting wire. Okay, so I repeat, since the terminal E is disconnected, then UBC is equal to UCD is equal to UDE is 0, so we deal with the lamps as if they are connecting wires. Okay, and this is reasonable because when the switch K is open, the lamps are switched off. So we are done with these, and now let's discuss the voltage UEF across the open switch and the voltage UFE across the open switch. We know that an open switch in series with the battery have the same voltage of the battery, so this voltage here will be either plus 12 volts or minus 12 volts, and this depends if you are measuring UEF or UFE. So notice that now because the switch K is open and this terminal E disconnected, so it's considered as a connecting wire, the potential at the point P is equal to the potential at the point E because simply this is a connecting wire. So this VE is equal to VP. Now moreover, between N and F we have a connecting wire, so the potential at the point N is equal to the potential at the point F. So here if you are measuring the voltage UEF, so it's equal to the potential at the point E minus the potential at the point F. Now notice that VE is equal to VP and VF is equal to VN. So this is equal to UPN, which is equal to 12 volts. So in this case UEF is equal to 12 volts. And this is simply because the point E is connected to the positive pole and the point F is connected to the negative pole. Since we are measuring UEF, which means that we are measuring UPN, which means that we are measuring a positive voltage, okay? Now what about the voltage UFE? Now simply if UEF is equal to 12 volt, then UFE is equal to minus 12 volt, but let's prove it using the fact that the point E is disconnected terminal, then it is considered as a connecting wire. So we are interested in the voltage UFE, which is equal to the potential at the point F minus the potential at the point E. Now the potential at the point F is equal to the potential at the point N because between N and F we have a connecting wire, minus the potential at the point E is equal to the potential at the point B because simply between A and P we have a connecting wire. Why? Because the terminal E is disconnected, so BE is considered as a connecting wire. So minus VP, so VE corresponds to VP, so this is equal to UNP, and we know that if UPN is equal to 12, then UNP is equal to minus 12 volts. So in this case UFE is equal to minus 12 volts. Then the last idea that we can add here, an open switch in series with the battery has the same voltage of the battery up to a plus or minus sign, depending if you are measuring from positive to negative terminal, or vice versa. And the important statement here that we must note out is the following: that a disconnected terminal can be considered as a connecting wire. This is very important, okay? So always a disconnected terminal can be considered as a connecting wire. Now let's move to the next important role of a switch is short-circuiting an electric component, and by this I mean switching on and off. So switching on and off an electric component. Now first of all, if you consider the following electric circuit, so we have two switches, K1 and K2. So what's the role of K1? K1, the main role of K1 is to switch on and off the main electric circuit, okay? So what about the switch K2? So let me first of all say the following note: a connecting wire connected only to one terminal can be ignored. Now suppose in this case we close the switch K1. Now K1 is a closed switch. So here in this statement I'm saying that a connecting wire connected only to one terminal can be ignored. So notice now the switch K2 can be considered as two connecting wires. This is the first connecting wire, and this is the second connecting wire. Okay, so here what I'm saying, a connecting wire connected only to one terminal can be ignored. Now if you consider the switch K2 as an open switch, so in this case, what is the switch K2 is doing? Is doing nothing, simply because a connecting wire connected to one terminal can be ignored. So this connecting wire is connected only to one terminal, so we can ignore this wire. And this connecting wire is connected to one terminal, which is the terminal E, so it can also be ignored. And in this case we can apply the analysis as we have done it previously, okay? Now what happens if you close the switch K2? So let me repeat the statement: a connecting wire connected only to one terminal can be ignored, so this wire can be ignored. A connecting wire connected only to one terminal can be ignored, okay? So now what about, so in this case this open switch is useless at this moment. Now if we close this switch K2, let me close it. Now in this case, what's the role of the switch K2? So notice that in this case the voltage UDE is equal to 0 because across D and E we have a connecting wire. But we can consider between the terminals D and E that we have the electric component D3. So in this case the voltage across the electric component D3 is 0 according to law of uniqueness of voltages, because the voltage across a connecting wire is 0. So here the role, so we have that UDE is 0. So what does UDE mean 0? That the electric component D3 is not functioning anymore, okay? So a short-circuited electric component has a 0 voltage. Okay. So in this case, what's the role of the switch K2? Short circuiting an electric component using a switch between brackets, which is equivalent to, say, connecting wire, turns off the electric component itself. So let's recap the main ideas. Now the switch K1 is to switch on and off the main electric circuit. What about the switch K2? In case where the switch K2 is an open switch, so this can be considered as a connecting wire connected to one terminal, so it can be ignored, as well as for this. So in this case, the electric component D3 is functioning normally. However, if the switch K2 is closed in this case, which means that the electric component D3 is short-circuited, so in this case UDE is equal to 0, and the reason is given by short circuit. What does this imply? Is that the electric component D3 is not functioning anymore. Okay. Now the final role of the switch is given by switching on and off a branch of an electric circuit. Now if you consider the following electric circuit, we have two switches K1 and K2. Suppose now we close the switch K1, but however we keep the switch K2. So what will happen to the lamp? What will happen to the lamps L1 and L2? So notice that this terminal is a disconnected terminal. Therefore, from this point to the point A, this can be considered as a connecting wire, because recall that a disconnected terminal can be considered as a connecting wire. And let me also highlight this statement. So I repeat, because this terminal is disconnected, now this can be considered as a connecting wire. Moreover, a connecting wire connected only to one terminal can be ignored. Notice that this connecting wire is connected only to one terminal, which is the point A, so it can be ignored. So simply we can, in this case, when the switch K2 is open, we can ignore this part of the electric circuit. We can ignore it all. And similarly for this part, since this is a connecting wire only connected to one terminal, so it can be ignored as well. Okay, and the circuit reduces to the following form. Okay, now as a direct application on what I have explained, let's consider the following exercise. Then exercise number 13, they are telling me document 3 shows an electric circuit consists of 3 electric loads D1, D2 and D3 that are identical. This is important. And connected to a DC voltage source of 12 volts. So in this case, the trick in solving such type of exercise is to write the voltage on the electric circuit itself. Then UPN in this case is equal to 12 volts measured from the positive pole to the negative pole. An electric switch K1 is connected between the battery and the load D1. Okay, another electric switch given by K2 is connected in parallel with the load D3. Now in number 1 they are telling me that the two switches K1 and K2 are opened. Okay, they are telling me, okay, so before we start answering the question, let's consider the switch K2. So now the switch K2 consists of two wires. So this is the first wire connected only to one terminal, so it can be ignored for the moment, whereas this wire is only connected to one terminal, can be ignored for this moment. Okay, so no need to discuss anything about the switch K2. As for the switch K1, so notice that an open switch in series with the battery have the same voltage of the battery. They are asking me what is the value of the voltage UAP across the open switch K1. So let's say an open switch in series with the battery has the same voltage of the battery. So in this case, UAP will be either given by plus 12 volts or by minus 12 volts, and this depends on how we are measuring the voltage. Notice that P represents the positive pole and A represents the negative pole. Notice that we are measuring from the negative pole to the positive pole, then in this case UAP is equal to minus 12 volts. Okay. Now in 1.2 they are telling me what's the value of UPN and UNP independent if the switch K1 is open or closed. We have that always UPN of the battery is equal to 12 volts and UNP, which is equal to minus UPN, which is equal to minus 12 volts. Okay. Now in number 2 they are telling me now the switch K1 is closed and K2 is open. So K2 is remaining open, no need to discuss it. Now in this case we are closing the switch K1 and they are telling me in 2.1 UPA is equal to 0. Justify. Notice that across the terminals P and A we have a connecting wire. So let's say the voltage across a closed switch is 0 since it acts as a connecting wire. So in this case UPA is equal to 0. So notice that previously the value of UPA, so the value of UAP was given by minus 12, so UPA is given by 12. The moment we switch the switch off, then the value of UPA becomes 0. Now in 2.2 they are asking me about the voltages UAB and UAN. Across A and B and A and N we have a connecting wire. So let's say the voltage across a connecting wire is 0. This is, so UAB is equal to UAN is equal to 0. So now before we proceed to 2.3, now since in 2.1 and 2.2 they are asking me about voltages across different electric branches, then we expect in 2.3 to ask me about the law of addition of voltages. Then indeed they are asking me about the voltage UBE. Then let's say apply law of addition of voltages. Then always on the left you write the voltage that you are interested in calculating, which is UBE. And on the other side of this equation, we will go across different electric components such that we know their voltages. We know UBA, UAP, UPN, and UPE. Then this is a valid equation because we have started with B, ended with E, and each letter we have inserted it twice, and everything is being justified. So if UAB is equal to 0, then UBA is equal to 0, plus UAP, plus UPN, which is given by 12, plus 0, and this is given by 12. Everything previously expressed in the SI, so the value of UB will be in the SI, which is volts. So UBE is equal to 12 volts. And now in 2.4, they are telling me deduce that the voltage across each load is given by 4 volts. And by deduce, it means that we need to use the part just previously before. In part 2.3, we have determined that the voltage, so UBE is equal to 12 volts. So what does UBE represent? UBE is the applied voltage between the points B and E. Across B and E, we have 3 components that are identical. So let me say, since D1, D2, and D3 are identical, then they have the same voltage. So here I'm saying that D1, D2, and D3 have the same voltage. Now let's formulate this mathematically. So what's the voltage of the electric component D1? It's given by UBC, which is equal to the voltage of the electric component D2, which is given by UCD, which is equal to the voltage of the electric component D3, which is UDE. And as we can notice here that this switch K2 in this case doesn't play any role. So now we can eliminate the point C, eliminate the point D. Then in this case, this is equal to UBE divided by the number of electric components that we have, and they are given by 3. Now the value of UBE is given by 12 divided by 3. Then this is given by 4 because 12 is expressed in volts, so the value of these voltages is given by volts. So in this case we have that UBC is equal to 4 volts, UCD is equal to 4 volts, and UDE is equal to 4 volts. Then indeed the voltage across each load is given by 4 volts. Now in part 3, they are telling me now K1 and K2 are closed. So the switch K2 is no more open, now it's a closed switch. So now in 3.1, they are telling me UDE is equal to 0 justified, so we can directly say UDE is equal to 0, and the reason is given by short circuited. Okay, so no need to justify and say that across D and E we have a connecting wire and the voltage across a connecting wire is 0. According to law of uniqueness of voltages, they have the same voltage. Directly we can state that UD is equal to 0, and the reason is given by short circuited. Now in 3.2 they are asking me deduce that UBD is equal to 12 volts, and by deduce it means that we need to use the part just previously before. In 3.1 we have determined the voltage across a branch, which gives us a hint that we need to use the law of addition of voltages. And always on the left, we'll start by the voltage that we are interested in calculating, which is UBD. And from B, we will go to A. From A to P. From P to N. From N to E. And E back to D. So we have started with B, started with B, ended with E, ended with E, and each letter we have inserted twice. Okay? So now UBA is equal to 0 justified. This is 0, this is 12, this is 0. Moreover, we have calculated that UDE is equal to 0. Whenever UDE is equal to 0, then UED is equal to minus UDE, which is equal to minus 0. Okay? So simply because that between A and D, the electric component D3 is short-circuited. Now this is equal to 12 volts. And now by short-circuiting the electric component D3 as if D3 doesn't exist anymore, okay? So it's not functioning anymore. Now in 3.3 they are telling me show that the voltage across the loads D1 and D2 is given by 6 volts. So we need to determine the voltage across this electric component and this electric component, knowing that they are identical. Since D1 and D2 are identical, then they have the same voltage. And this can be formulated in the following way. The voltage of D1 is given by UBC, which is equal to UCD, the voltage of D2, which is equal to UBD. So we eliminate C and we divide by the number of components we have, which is 2. So this is equal to 12 divided by 2, which is equal to 6 volt. So as you can see that the role of the switch K2 is to eliminate the electric component D3 and increase the applied voltage across the electric components D1 and D2. And this is the idea reflecting section 9.2. Okay? So it's the same electric circuit. Now we have reached a new section, which is section number 10, direction of electric current. Till this moment in this section, what we have discussed is only the voltage, but we know that another important property in an electric circuit is given by the electric current. We know that whenever we have a closed circuit, then it will be traversed by an electric current. So what's the relation between electric current and the voltage, or in particular the sign of the voltage with the direction of the electric current? So here let me consider the following values. Suppose that, let me increase the size of this document. Okay, before we refer to the following document, let me explain the following. Now suppose here we have an electric component consisting of 2 terminals, and suppose that this electric component is connected to another closed circuit in which this is the terminal A and this is the terminal B. And suppose that in this case we have that UAB, say for example it's a positive value, it's given by 3 volts, which is positive. Okay? So now we may ask the following question. What is the direction of the electric current? Is it from the point A to the point B, or from the point B to the point A? And this for sure depends on the sign of the voltage UAB. Now first case, if UAB is positive, which means that VA minus VB is positive, which means that the potential at the point A is greater than the potential at the point B. So if the potential at the point A is greater than the potential at the point B, then the electric current is traversing this branch from the point A to the point B. Okay? Done? So always the direction of the electric potential is from the point of higher potential to lower potential. For this reason, previously we were interested in calculating, in determining which terminal is of higher potential. Okay, now the second case. Second case, if you consider the same electric component of terminals A and B, and let's say the following: if UBA is positive, which means that VP minus VA is positive, VB minus VA is positive, which means that VB is greater than VA, then the direction of electric current will be from higher potential to lower potential. From B to A. So in this case we can generalize and say, so this is very important, across a closed circuit, the direction of electric current is from higher potential to lower potential. Okay, as a direct application, let's consider the following electric circuit, and let me here label some voltages. So let me say that UAB is equal to 4 volts, UDN is equal to 4 volts as well, UCD is equal to 6 volts, UPA is equal to 8 volts. So we have seen previously how to calculate these voltages. UAC is equal to 6 volts, UBC is equal to 2 volts, and eventually UAD is equal to 12 volts. And we are interested in determining the electric potential in the following electric circuit regardless the poles of the battery. Okay, so now we know that always the electric circuit, the direction of the electric current is from the positive pole to the negative pole. Here, regardless of the battery, we need to determine in each branch the direction of the electric current. So starting with P and A, we know that the voltage UPA is positive, which means that the potential at the point P is greater than the potential at the point A. So in this case, the direction of the electric current will be like this. Now if you consider UAB, UAB is positive, which means that VA is greater than VB, which means that the direction of the electric current will be from A to B. Now if you consider UBC, so UBC is positive, which means that VB minus is greater than VC, so the direction of the electric current is from the point B to C. Now if you consider UAC is positive, which means that VA is greater than VC, so the direction of electric current is from the point A to the point C. Now finally, as for the electric component across C and D, we have that UCD is positive, which means that VC is greater than VD, then the direction of the electric current is from C to D. Now as for the electric component across D and N, we have UDN is positive, so VD is greater than Vn, so the direction of the electric current will be from the point D to the point N. Okay, so knowing the voltage across a branch, we can determine the direction of electric current by knowing that whether this voltage is positive or negative. And the final section in this chapter is given by section number 11, sweeping in DC voltage. So we know that this is the screen of the oscilloscope. Now suppose that we have a luminous line spaced upward. So we know always that a DC voltage is represented by a horizontal luminous line. So this is a positive DC voltage. Now if the luminous line is at the center of the screen, so this is 0 DC voltage. And in the case where the luminous line is displaced downward, we know that this is a negative DC voltage. And all of these cases occurs for the section 11.1 is when the sweeping is on. So in this case, we observe the following luminous line on the screen of the oscilloscope simply because the sweeping is on. Now what happens if the sweeping is switched off? So sweeping is off. So now we are interested in the same cases. So let me here say positive DC voltage. Zero DC voltage. Negative DC voltage. So in this case, we will observe a luminous line, a luminous point displaced upward. In this case, we will observe a luminous spot at the center of the screen, and in this case, we will observe a luminous spot. So if I consider the same value, so if this is displaced 2 divisions upward, so the luminous spot will be here. This will be at the center. If this is displaced, let's say for example 2.4 divisions downward, so this point will be here. Now what's the reason between, okay, so what's the reason that we are observing a spot? The sweeping means that this spot will move. So when the sweeping is on, now if the sweeping is switched on, what will happen actually that this spot will start to move from left to right. It will start move like this. Then it will reaches this point, then again it will reaches this point, and it start moving from left to right, from left to right. As this luminous spot is moving from left to right continuously, then it's sweeping the screen. Okay, so in this case the luminous spot, the shape of the luminous spot will be a luminous line. Okay, so whenever the sweeping is off, so the luminous spot stopped to move, it will stop to move, so it have stopped moving, and in this case we will observe only a spot. Okay, so in the case of positive DC voltage, a luminous spot displaced upward, and the reason why it's displaced upward because the voltage is positive. It is a luminous spot and not a line because the sweeping is off. What causes this spot to be a line is when we turn on the sweeping. Okay, a luminous spot displaced upward. In the case of 0 DC voltage, a luminous spot at the center of the screen, and negative DC voltage, then in this case we will observe a luminous spot displaced downward. And now let's solve the following exercise. Exercise number 14. They are telling me the adjacent figure represents the combination of 5 identical lamps which are connected to a DC generator, a digital voltmeter that indicates minus 12 volts, an oscilloscope, and an oscilloscope, okay, are connected across the terminals of the generator. Now in number 1 they are telling me indicate the voltage measured by the voltmeter, then deduce the voltage across the terminals of the generator. So notice that the voltmeter will measure either UPN or UNP because its two terminals is connected across P and N, but this depends on the COM terminal. And let's say since the COM terminal is connected to P, and the other terminal is connected to N, then the voltmeter measures. Okay, so in this case it's measuring U, the voltage U, so always the COM terminal is for the second letter, so this is P and this is N. So always the COM terminal is for the second letter. And in this case, because the voltmeter is measuring minus 12 volts, so we have that UNP is equal to minus 12 volts. Okay. Now in this case they are telling me deduce the voltage across the terminals of the terminals of the generator. So if UNP is equal to minus 12 volts, then UPN is equal to 12 volts. Okay. So this is the voltage across the terminals of the generator. Now in number 2 they are telling me we observe on the oscillogram, which is the oscilloscope, a luminous line displaced by 4 divisions. Then Y will be either plus or minus 4 divisions. Now in part A they are telling me indicate with a justification whether this line is displaced upward or downward. And in order to do so, indicate means that we need to state with a justification. In order to do so, we need to refer to this document and to check whether the oscilloscope is measuring UPN or UNP. Notice that since the phase terminal is connected to P, and the mass terminal is connected to N, then the oscilloscope or the oscillogram measures UPN, which is positive. Since the measured voltage is positive, then the luminous line will be displaced upward. And here, since we have a luminous line, which means that the sweeping is switched on the oscilloscope. So in this case, we have y is equal to plus 4 divisions. So they are telling me what would we observe in the absence of sweeping. We know that we will observe a luminous spot. This luminous spot will be either displaced upward or at the center or downward, and this depends on the sign of the measured voltage. So let's say, since the measured voltage is positive and the sweeping is off, then we would observe a luminous spot displaced upward. Okay, now in part C they are telling me calculate the vertical sensitivity of the oscilloscope. We know that the voltage, the vertical sensitivity, and the value of y are related via the following formula. U is equal to SV multiplied by y. Knowing that we are interested in determining SV, so flipping this equation, we have that SV multiplied by y is equal to U. Knowing that we are interested in determining SV, so moving y to the right hand side of this equation, it will be divided. Then SV is equal to U divided by y. The value of U is given by 12. The value of y is given by 4. Plugging this on the calculator, then the value of SV is given by 3 volts, either per division or per centimeter, and this depends on the unit of y. Since y is expressed in division, so this is volts per divisions. Then the vertical sensitivity of the oscilloscope is given by 3 volts per division. Now in part 3 they are telling me calculate the potential difference across each lamp. So now, since we have started voltage analysis, let me write that UPN is equal to 12 volts. Knowing that all of these lamps are identical, in order to determine first the voltage across the lamps L1, L2, and L3, we need to determine the voltage across the points A and D. So let's say apply law of addition of voltages. Knowing that first we are interested in determining the voltage L1, L2, L3, therefore we need to calculate the voltage UAD, which we will place on the left. And on the other side of this equation, we'll go from A to D across different electric components such that we know their voltages. For example, we can go from A to E, E to D, but we don't know the voltage across L4 and L5. A more convenient way is to go from A to P, P to N, and to D. So UAP plus UPN plus U and D. Now across A and P we have a connecting wire, so UAP is equal to 0, and the reason is given by a connecting wire. Plus UPN, which is equal to 12 measured already, and U and D is equal to 0, and the reason is given by a connecting wire. So this is equal to 12 volts. Now we have to determine the voltage across the lamps L1, L2, and L3. Now we can safely say, since L1, L2, and L3 are identical, then they have the same voltage. So how this can be formulated mathematically? The voltage across L1 is given by UAB. The voltage across L2 is given by UBC. And the voltage across L3 is given by UCD. Notice that if we eliminate this point, we are left with the voltage UAD, which we have already calculated. Then UAD divided by the number of electric components we have that are identical, which is given by 3. So this is 12 divided by 3, which is equal to 4. Since this is expressed in volts, so this value will be expressed in volts. Then let me say that UAB as a first step is equal to 4 volts. UBC is equal to 4 volts. And UCD is equal to 4 volts as well. And the trick in solving such type of exercise is to write applied voltage on the electric circuit itself with their labels. So UAB is equal to 4 volts, UBC is equal to 4 volts, and UCD is equal to 4 volts. Now it's remaining to find the voltage across L4 and L5. So we are done with this. Or let me do it here. Now notice that the applied voltage between the terminals of L4 and L5 that are given by A and D we have already calculated, and it's given by 12 volts, so no need to repeat the steps. And let's say in this case, since L4 and L5 are identical, then they have the same voltage. And in this case, the voltage across the lamp L4, which is given by UAE, is equal to the voltage across the lamp L5, which is given by UED. And this is equal, if we eliminate the point E, we are left with UAD. The value of UAD we have calculated, which is given by 12. Sorry, here we divide by the number of electric components that we have, and it's given by 2. So it's 12 divided by 2, which is equal to 6. So, and this is expressed in volts. Then UAE separately is equal to 6 volts, and UED is equal to 6 volts. And the trick here is to write this applied voltage here. So UAE is equal to 6 volts, and UED is equal to 6 volt. Now finally in part 4, they are telling me determine the potential difference UCE, and for sure this can be done using the law of addition of voltages. Knowing that we are interested in determining UCE, then let's start by UCE. Now we need to go from C to E across different electric components such that we know their voltages. We have two ways. We can go from C to B, B to A to E, but this is a long path. A shorter path is going from C to D, D to E. Then from C to D and D back to E. The value of UCD is given by 4. Now notice that if UED is equal to 6, then UDE is given by minus 6. This is equal to minus 2. Since both of these quantities are expressed in the SI, so the value of UCE will be in the SI, which is volts. Then UCE is equal to minus 2 volts. And we are done with this exercise. So that's it for me in this video, guys. In the next part, we'll complete solving exercises on this chapter.